you. And so today I'll be telling all the participants of this ISRO START program, which I think is a great initiative, and I'll tell all of you a little bit about the moon. Okay. Now, of course, this is a very broad topic, and I was also briefed that we have participants from very different academic backgrounds. And so I'll try my best to actually get a few important ideas across, which hopefully will promote or excite some of the participants to take up moon as a topic of research in the future. So I'll tell you a little bit about origin of the moon, the ideas that were there and the ideas that we believe are correct today. I'll tell you about time constraints, formation of moon, lunar rocks, and then a little bit about what the moon is made up of, both in terms of rocks and in terms of composition, and put forth the idea of this lunar magma ocean that has been there. And finally, I'll pick and choose some geochemical and isotopic tracers to basically kind of highlight how we study different lunar processes. And so if one has to look at some keywords, we'll talk about origin, the age, constitution, and composition of the moon, and eventually talk about some lunar processes. And so, of course, the moon has been, a topic of fascination for humans long before, research started, right? And so I picked up this phrase from this book by Bevan French, saying that, look, the moon has been a timepiece that early man actually used to evolve from a wandering hunter to a settled farmer. And indeed, this waxing and waning of the moon has given rise to what is known as a calendar. And of course, there were other calendars that are prevalent too. But the lunar calendar has been primarily used to basically convert man into a farmer, right? Or human into a farmer. And so we knew when to plant seeds and when to harvest them, primarily looking at the moon. And people converted, the 365, days into months and so on and so forth, primarily based on looking at the moon. And it's not surprising that the moon has been a topic of interest for different cultures, ancient cultures and modern cultures. And so the Babylonians called the moon the Sin, and the Greeks called them, Selene was the moon god, and the Romans gave rise to the term Luna, and of course Chandra and Soma are terms used for the moon in Sanskrit, and other languages that have a root in Sanskrit. And then of course Diana, Artemis, Cynthia, and of course the Chinese god of moon is called Changi. Now, of course, this term Selene is highlighted out here because the study of the moon broadly is actually called selenology, and the root of that word comes from Selene, which is a Greek god for the moon. So let's look at what ideas were prevalent before the Apollo missions about the origin of the moon. The first one was, of course, the moon was a little planetary object that was captured by the Earth, and this is coming from the 1950s. This talked about the tidal evolution of the Earth-Moon system in general. And it is true that the moon was actually much closer to the Earth in the past, which was about, it was derived from within the Roche limit, which is about, 3 times the Earth's radii. And today the moon is much farther away, about 60, Earth radii. But, over time, there's this theory actually is a very low probability, because it clearly depends on the moon's initial orbit. Okay. And so it's very hard to, accept this, theory, although it's remained a very important one. There was also ideas of the moon and Earth evolving as a binary planetary system, just like a binary star. And so the idea was that both the Earth and the moon, they form close to each other and they keep orbiting one another. Now, of course, Harold Urey, and this was actually proposed by none other than Kuiper. And so, the Kuiper belt comes from, this gentleman, right? So, but Harold Urey and others, they basically said that, look, this is a very restrictive scenario because to have both of these bodies, orbiting again, around each other would eventually lead to collision or, escape of one body. And so this is, again, not a very, easy idea to believe in. There was also this idea of fission and precipitation, and which is essentially means that the moon came out of the Earth, and the Earth-Moon system originally combined into a single body, which rotated with a very low periodicity. But then there was these resonance effects, and they led to a tidal bulge, which was unstable, and that bulged out material was ejected from the Earth's mantle to form the moon. This was there from the late 1800s, Darwin and others, and so, but rejected by Jeffreys clearly in 1930, but was actually brought back into discussion by none other than Ringwood. And remember, these are all pre-Apollo missions, right? So because Ringwood started looking at different ideas and says, look, I mean, the moon most likely came out of the Earth. Okay, and so he kind of believed a form of this fission hypothesis, and this was also taken forward by other very, very famous scientists like Cameron and O'Keefe, and so these are just some of the years in which these ideas were kind of prevalent. But of course, then Apollo 11 happened, and so this was 1969, and this is just the Saturn V. The launch vehicle. And if anybody ever go to Lunar Planetary Science Conference and you go to the LPI, you actually have this entire Saturn V displayed out there. So it's a humongous feat of engineering, right? So anyway, among other things that happened, many of you might have read this children's book called Cow Jumping Over the Moon, and so this is a bit of a joke out here. So this is this astronaut, saying that Houston, it seems like the cow that initially jumped over the moon didn't quite make it. So jokes aside, there were actually significant developments that happened in our understanding of the moon. And one thing is, it basically created an interest. Now, of course, these lunar missions were all, born out of this race, arms race, or space age race between USSR, the former USSR, and United States. But even though the environment was that of war or Cold War, what came out of this kind of environment was something very exciting, and people started studying the moon. And so they started studying the impact craters on the moon. They found out that craters on the moon were of a variety of sizes, from microns in lunar soil to thousands of kilometers in diameter. The South Pole Aitken Basin is really big. And so these craters could be simple craters, like simple basins, to maybe something like a complex crater, which actually has central elevated areas, to these ring-like structures, which are found in really large structures. And we'll talk about crater counting and how that actually tells you something about lunar crustal ages over time. But what it actually, this whole study of crater counting actually somewhat accidentally gave rise to another idea about the origin of the moon. And this comes from the University of Arizona, where this gentleman Hartman was actually a PhD student of none other than Kuiper. And when he was actually working on what is known as the rectified lunar atlas, which is actually shown on the left panel out here, and he was actually studying these giant ringed impact craters, especially one called Mare Orientale. And he basically came up with this idea, along with Davis in 1975, that maybe the moon basically captures these evidences of large-scale collisions. What about the moon actually forming because of collisions? And this gave rise to this giant impact theory, which basically was initially proposed by Hartman and Davis, but again picked up by Cameron and Ward in two subsequent papers. And the idea is that you had a Mars-sized impactor called Theia, which basically came and collided with the proto-Earth, and that basically gave rise to the moon. But these models also suggest that the moon, if this model is correct, should be mostly made of the impactor because of the angular momentum constraints of the Earth-Moon system. And we will see whether that is possible or not later in this presentation. And of course, this was picked up by, well, let me just see if I can get rid of this. It seemed to be working earlier, but anyway, just 1 second. Yeah, there you go. So these are smooth particle hydrodynamic simulations that were put forward by Robin Canup and Asperg in 2001. The idea was that if you had a Mars-sized impactor, now Mars has an implication in the sense that the impactor was also differentiated. And by differentiated, I mean that there's a body that has a core that is separate from the silicate mantle, right? And so this the simulations basically showed that yes, it is possible to have most of the moon formed from the impactor, but the core of the impact, the metallic part of the impactor, which is shown here in these red dots, essentially came and kind of combined with the metallic part of the core of the proto-Earth. Okay, so well, all of these things were somewhat interesting, but it also gave rise to the general idea about planetary accretion. Because of the study of impact craters on the moon, today we believe that planets actually accreted, or planetary bodies actually accreted with what is known as this hierarchical accretion in a model, which allows for simultaneous growth of a planetary body and differentiation of a planetary body. So that means, while core keeps forming on these planetary embryos, they also start colliding with each other and form bigger and bigger, planetary objects. And one of the last stages of, let's say, accretion of the Earth would be in a collision of the proto-Earth with this Mars-sized impactor, Theia, which eventually have, create the Earth-Moon system. Now, collisions become very important because these are very important heat sources, as shown here in this diagram on the right. You can instantaneously raise temperatures to beyond the melting point of silicates, and also in some cases metals. And so it becomes very important heat sources, which is necessary for planetary differentiation to separate the metal from the silicate, especially for larger planetary bodies. For smaller planetary bodies, collisions are not that important. You need what is known as short-lived radionuclides. Anyway, so the Apollo 11 and subsequent Apollo missions actually brought back a lot of lunar samples. And this is what basically gave rise to different theories about the moon and its origin and evolution over time. So there were 6 Apollo missions, which are shown here on the left, which brought back about 380 odd kilograms of lunar rock, which is a humongous feat. And then around the same time, you also had missions sent by the USSR called the Luna missions. They also had 3 successful sample return missions, but they brought back about 300 grams of rock. And then there was somewhat of a hiatus for about 50 years, until about 2 years ago when the first mission from China, the sample return mission, Chang'e 5, brought back samples about 1,700 grams or so. In addition to the lunar samples that have been brought back, we also have over 300 meteorites, which basically are derived from the moon. So this means these are a result of collisions with other planetary objects on the moon, and that basically kind of ejects some debris, which, if they escape the escape velocity of the moon, and eventually enter the Earth's orbit and survive the burning in the atmosphere, eventually hit the Earth's surface, and that's when it becomes a meteorite. And so we also have other material from the moon in the form of lunar meteorites, right? And so when we started studying all these lunar rocks, since the late 1960s, we actually unearthed, several things, including, the different rock types, the topography on the moon. And so if you look at all the lunar samples that have been studied, they are mostly coming, classified into 4 types. Some are these pristine highland rocks. Highlands means that the topography is high, right? And these are primordial igneous rocks, like volcanic rocks, like the ones that we have even on the surface of Earth. And these have not been contaminated by, subsequent mixing by, impacts. You also have, primordial basaltic volcanic rocks from these darkish regions called the mare regions. These are primarily lava flows, like, let's say, you had on Hawaii, you see it in Hawaii every now and then. We had it in the Deccan Traps earlier, 65 million years ago. So these are lava flows. They also have, some explosive, deposits called pyroclastic deposits. In addition to these pristine end members, you also have a lot of brecciated material. Things have been fractured and broken up. You also have molten material, like the impact melts that have been quenched quickly. And because of high temperatures resulting from collisions, you can actually do phase changes, mineralogical changes. And those are, so these thermally metamorphosed granulitic breccia. And finally, the lunar regolith, which is essentially the lunar, soil. And within, the soil, you also have brecciated material called the regolith breccia. So all of the lunar samples that we have thus far can be, categorized into these 4 different types. And so if you look at the topography, this is primarily data from the lunar near side, okay? You will find that, you can either have these flat, regions that are dark and, basalt rich, called the Mare region or the Maria. And then you have the highlands, which are mostly feldspathic, in composition. And of course, the far side of the moon is also dominated primarily by the highlands type crust. Okay, so you have the Mare basalts, which are volcanic rocks. Volcanic means that, the magma actually came on the surface, right? And then you have the highland that are the terra, which are also, mafic rocks mostly, but they are mostly plutonic. That means the melt actually kind of condensed at slightly greater depths, okay, or rather cooled down at greater depths. So these are extrusive forms, and these are more like intrusive forms, right? And if you look at it in slightly greater detail, the Mare basalts, based on their composition, can be classified into what are known as high titanium basalts, the low titanium basalts, and the very low titanium basalts. And we label them this way because remember, we always have to compare it with what we see on the Earth, right? So these lunar basalts have very high iron and titanium concentrations relative to terrestrial basalts. They have another very important feature, that is the depletion in alkali elements which are volatile, like sodium and potassium. And later in today's presentation, I'll bring back potassium again. These rocks also, if you look at their rare earth element patterns, they actually have what is known as a negative europium anomaly, and that is not seen in basalts on the Earth. They're actually seen in, let's say, granites on the Earth. Okay, and then there are these specific type of basalts called the creep basalts. The creep is just an acronym for basalts with high potassium, rare earth elements, and phosphorus. They also have very high thorium. And most of these rare earth elements are actually hosted in calcium phosphate minerals within these basalts, and these are called apatites and metallites. So if you look at all the Maria, you can actually, the basalts are essentially of these types compositionally. And then if you look at all the highland rocks, which is essentially 60% of the lunar surface, and you just look at two geochemical indices. One is the molar ratio of calcium divided by calcium, sodium, and potassium. Another one is a molar ratio of magnesium divided by magnesium plus iron. So some of these rocks have been labeled as ferroan, anorthositic suites, or the fan type of rocks. So what we have out here, well, some of you may not have a background in geology, but we'll keep it simple. There are only about 3 or 4 minerals which basically control, the rock compositions that you find in the highlands. One is a plagioclase, which is it could be a solid solution between sodium, potassium, and calcium aluminum silicates. But in the moon, you mostly find calcic plagioclase. That means calcium-rich plagioclase. And if you have a rock that is primarily made up of calcium-rich plagioclase, you call it an anorthosite. If you have a little bit of calcium-rich plagioclase and you add some, magnesium-rich material, like a calcium-magnesium, silicate, or iron magnesium silicate, you can actually make what is known as a pyroxene, which is another mineral. And so the rocks are anorthosites and anorthositic gabbros. If you look at the rocks which are very high magnesium by Fe, or high magnesium over magnesium plus iron, you're essentially looking at rocks with very high olivine. So these are, again, Mg2SiO4. And if you have mostly this magnesium rich silicate, you call it a dunite, or this unique rock called troctolite, which has some olivine and some plagioclase. Or let's say a gabbro, which is a plagioclase and a clinopyroxene, or a troctolite, which is a norite, which is a plagioclase and orthopyroxene. Anyway, so those are minor details, but you have these ferroan anorthosites, the magnesium suite, the alkali suite. Now, alkali suite is very rare because these are, although they call it alkali rich, these are rich compared to the general depletion in alkalis that you find on the moon. Okay. And these actually require the original melts to have been, rich in, this creep-like component. We have very, very rare granitic rocks called the lunar granites. Now, if you look at the continental crust on Earth, it's mostly granites and granodiorites, but the moon crust has very rare amounts of granite. And then, of course, the brecciated material, that is, the lunar breccia, right? So these are all the rock types that we'll ever discuss about in this presentation. And if you look at, again, a different way, geochemical, if you look at just the iron concentrations in the moon and the thorium concentrations of the moon, you'll actually find that there are two major, surface terrains on the moon. One are these creep-rich terrains, again, rich in potassium, rare earth elements, and phosphorus. They also have iron. They also have high amounts of thorium. And, and thorium, remember, is a radioactive, some of the 232 is a radioactive nuclide, right? So it's a heat-producing element. And 30% of the moon's heat-producing element is actually in this creep terrain, which is this procellarum creep terrain, as they call it. The other terrain that we have is, again, these feldspathik highlands, which, again, have low iron and also low concentrations of thorium. So just based on these two, geochemical indices, you can actually argue that most of the moon is either highlands or they're mostly, these creep-like structures, okay? So with that, we've now seen a unique assortment of rocks from the moon. So we basically found the anorthosites, we found basalts and gabbros and norites. We also found troctolites. And in terms of minerals, we basically had olivines and orthopyroxenes and clinopyroxenes and plagioclase and rare amounts or small amounts of what is called ilmenite, which is an iron titanium oxide, and quartz, which is silica. And so to explain this unique assortment of lunar rocks, one had to propose what is known as a lunar magma ocean, the idea of a lunar magma ocean, or LMO, which means that soon after accretion of the moon, so there must have been a very rapid accretion. Of course, when you accrete, a lot of material together and make them come together as a solid body, and then also start differentiating, between the heavier metals that go towards the center and the silicates, tend to be, moving away from the center, you actually release gravitational potential energy, and that also causes melting. So this large-scale melting of the proto-moon, of course, then the melt has to, kind of cool down and crystallize new material. Now, for many of you who are aware about crystallization of different minerals, when you have a basaltic melt, you'll find that this is called a Bowen's reaction series. You find that, minerals like olivine and orthopyroxene, they actually crystallize first from this melt. Okay, and these are, again, iron and magnesium rich, so they have slightly high density. So they kind of settle down to the bottom of this magma pile. And then what is left is basically material that is much more enriched in aluminum and silica. These are lighter, and that gives rise to minerals called plagioclase, right? And so what we end up having is a layered structure in the mantle, which is what is known as a cumulate mantle. And so for the moon, you basically had olivine and orthopyroxene rich rocks at the bottom, and the top was lighter material like plagioclase. But when you cool down the magma temperatures, the last minerals that actually crystallize out are, ilmenite and quartz. Now, these are two unique. This is silica, this is iron titanium oxide. Now, of course, if you have ilmenite sitting on the top of this cumulate mantle, there is a bit of a density issue because ilmenite is significantly more dense than olivine and orthopyroxenes and plagioclase. So there is something called density overturn of this ilmenite-bearing cumulates. And so that's how the moon's mantle essentially formed. You had, this liquid, mush that started crystallizing, firstly olivine and orthopyroxene material, and eventually, clinopyroxene and some plagioclase-rich material, and maybe the ilmenitic material on the top, which overturned. And so the lightest material, like anorthosites, actually stay on the top, and then the heavier material at the bottom, right? And so based on age constraints that we have, which we are going to discuss in another 2 or 3 minutes, one can argue that this entire lunar magma ocean crystallized within 200 million years or so. Okay, now we have a mantle, and just like the terrestrial mantle, which melts to form basalts, like in the mid-oceanic ridges, the lunar mantle must have also melted to form what are known as the mare basalts, right? And if you remember, in those mare basalts, you also have composition and heterogeneity in terms of low titanium, high titanium basalts, and Greek basalts. And so basically, when you look at all the rock types, the anorthosites are explained, the troctolites are explained, and eventually the mare basalts are also explained, right? So this is, this idea of a lunar magma ocean that we could invoke only after the samples were returned from the moon, and we found the unique, minerals that are actually present in the lunar rocks. Okay, so that's all about the lunar magma ocean that crystallized to form the mantle of the moon. Next, let's talk about the different rock types that we have already analyzed and how we determine the ages of these lunar rocks. I'm going to digress for about 3 minutes or so just to tell you that the ages of these rocks are mostly determined using radiometric age dating techniques. And if you look at the periodic table of elements that we have several elements like, let's say, samarium out here, or lanthanum or rubidium, which has multiple isotopes, but there are some isotopes that are actually radioactive. And an example would be, let's say, 87 rubidium, which decays to the radiogenic daughter of 87 strontium. And I'm going to take that example up soon. We also have other examples like, uranium-238 or 235 that decay to stable isotopes of lead with a lot of intermediate nuclides in between. We have 147 samarium that decays by alpha decay to 143 neodymium. But let's consider this pair, 87 rubidium decaying to 87 strontium. And so, of course, the law of radioactive decay is known to all of you. The rate of change of nuclides at any point of time is proportional to the number of nuclides of the parent. And so the proportionality constant is lambda. And the negative sign is because you're losing the number of parent nucleus are actually decreasing. And if you integrate this particular equation, make it dn by n is equal to minus lambda dt, and integrate from n naught to n and t naught to t, you basically get this form, which is the commonly seen radioactive decay equation, right? And so, of course, it also gives you an idea of half-life. That means that n is at any instant of time half of the initial amount of n, that is n naught, then that gives you an idea of half-life, right? Which is 0.693 by lambda. And so, there are different nuclides we talked about, which is very different half-life. These are of 147 samarium, 100 billion half-life. 87 rubidium was 49 billion year half-life. 238 uranium, 4.5 billion year half-life. Of course, for many of you who don't deal with radioactive nuclides, you must have heard still, carbon-14, right? Carbon-14 is, a dating technique that people use, but note that its half-life is about 1,000 years or so. So this is a half-life of about 6,000 years, right? So remember that, T half is inversely proportional to lambda. So longer the half-life, smaller is the decay constant. And you also have to remember a thumb rule, and that is, if you want to date something that is more than 5 times, which you think is older than more than 5 times the half-life of the nuclide that you're trying to use, you're possibly using the wrong one. So if you're trying to detect something that is old, of the order of billions of years, you shouldn't be using, a carbon-14, because 5 times the half-life is only going to give you about 30,000 years or so. So this is very good for dating wood chips and stuff like that, trees which formed or lived only the last few tens of thousands of years, right? But when we talk about planetary objects and dating them, we actually go to these nuclides which have very, very long half-lives. And let's consider the example of 87 rubidium decaying to 87 strontium. And there is a small trouble out here in the sense that, again, a bit of a digression from the topic, but an important one. And that is, we cannot use this equation the way it is. Because remember, our sun, which is about 99% of the mass of our solar system, is a very young star, right? It's only undergoing hydrogen burning to form helium. Now, you might wonder, where did all the heavy nuclides like uranium or rubidium or samarium or even carbon, where did they come from? Our sun is not really making any of those, right? And this is where, one has to quote, Carl Sagan, rather paraphrase him by saying that we are all made up of stardust, right? Because all the heavy nuclides are part of the interstellar media, which has been, so to speak, contaminated over time by, the supernova explosions of larger stars whose core temperatures were high enough to actually form, elements up to iron by nuclear fusion. And eventually, when the supernova explosion happens, you can rapidly add neutrons, by what is known as the R process to actually produce nuclides that are as heavy as uranium and above, right? So when we look at all these elements, these are actually elements that were produced in the interstellar media. And so when we try to look at strontium-87, which is a decay product of 87 rubidium, there is also already a little bit of strontium-87 that was there when our solar system formed. That is the D naught. So when we're looking at the radiogenic daughter, because we're looking at the parent-daughter decay system, we have to subtract the initial amount. And of course, one atom of the parent decays to one atom of the daughter. So the Ds and D naughts can be converted to N naughts and N. And of course, we have this relationship from the last slide. So eventually, by simple arithmetic rearrangement, we get to this form where the total number of daughters of a particular nuclide are the initial number of daughters that were already present when the system started, plus N, which is the number of atoms of the parent, times e to the power lambda t minus 1. So if you consider the decay of 87 rubidium to 87 strontium, you have the same form. N is equal to, D is equal to D naught plus N times e to the power lambda t minus 1, right? And so we can use this particular equation, but the problem is when you try to measure, these particular the sample, transmitting the sample through. So there are efficiencies, ionization efficiencies, transmission efficiencies, which are never constant. And so absolute concentrations can vary, but what will not vary is if you kind of normalize both sides of the same equation by something that is constant. And in this case, we will consider 86 strontium, which is a non-radiogenic but stable isotope of strontium. That means its concentration in this particular system is not changing over time. Now we can take a sample and measure its rubidium by strontium ratio and then multiply by the natural abundances of these isotopes to get this particular parameter. You can also take the left-hand side and say that this is in a sample, this is what we can measure in a mass spectrometer very easily, right? So you're left with the equation of a straight line. Y is equal to mx plus c, but you have two unknowns out here. Lambda is known for 87 rubidium, but t is what we are looking for, the time. We also don't know what was the initial amount of 87 strontium by 86 strontium in the system. Actually, let's say if you have a rock, which basically has a few minerals, and the minerals crystallize out of a magma. Let's say the lunar magma ocean, and that is what we're trying to date, right? So even before you started adding 87 strontium that is radiogenic because of decay of 87 rubidium, you already had some 87 strontium that was there in the system, right? So this is unknown. T is unknown. And so one equation, two unknowns, we need to apply a graphical method maybe. And so because this is the equation of a straight line where this is an independent variable, right? But this is a dependent variable because the concentration of 87 strontium, which is the daughter, depends on the concentration of the number of atoms of the parent, right? So we can take the schematic diagram and have 87 rubidium by 86 strontium on the x-axis and 87 strontium by 86 strontium on the y-axis. And let's say the system started off with three different minerals, A, B, and C. That is at time t equals t naught. The important thing is we want A, B, and C to have slightly varying 87 rubidium by 86 strontium ratios. And then we allow the system to progress over a particular period of time. So the concentration of A, the rubidium in A has gone down and it has become A1 at the expense of decay of 87 rubidium to form more strontium, right? So you have less 87 now, but more 87 strontium. B becomes B1, C becomes C1. And, the slope of these green lines are always going to be -1 because, one atom of the parent decays to one atom of the daughter. And so the slope of this line, if you again look at this, equation of the straight line, is nothing but e to the power lambda t minus 1. So lambda is known for 87 rubidium, so now you can determine t. So when you take a sample, like the lunar samples today, you basically separated three minerals, let's say A1, B1, and C1. You can measure their rubidium strontium ratio. You can also measure the 87 strontium by 86 strontium ratio in the samples. And when you have these 3 points, you can use a graphical method, or today we use these regression techniques, least squares regression techniques. We can actually get the slope of this line, and from the slope of this line determine t. Right, so this is what is known as an isochron diagram. And this is just to tell you that you can do it for rubidium strontium, you can do it for samarium niobium dating, uranium lead dating, and the different radiometric dating techniques. So with that, let's now move at some and take a look at some real data. And this is, just some data that I found from the NASA website, where you find that the ton of these Mare basalts, which are hovering at an age of 3,700 to 3,200 million years. Okay, so this is all in millions of years in times 10 to the power 6, or 3.7, 3.2 times 10 to the power 9. That's billion. Then you have some very old rocks, these plagioclases from the highlands. anorthosites from highlands, some creep, which are, almost the age of the Earth, 4.5, 6, 7 billion years, some zircons. So if you take the average, ages of highland rocks, you find that they're older, about 4.4 billion years, compared to the average of the Mare basalts out here, that's about 3.5 billion years. And so clearly, when you look at, the extended data that we have, the moon definitely had, volcanism between 3 billion years and 4.5 billion years ago. Because remember, these are all products of melting of the lunar mantle, right? And the lunar mantle formed by crystallization of the lunar magma ocean. So to form these basalts, you must have melted the mantle and the magma came up, just like, you have volcanism on Earth. So this is what was the state of our knowledge of lunar volcanism until a couple of years ago, okay? And so we basically thought that, you had evidence, only for lunar magmatism, only up to 3 billion years or so. And so this is, how, some of these timelines would look like until 2 years ago. So remember that, the age of the solar system, again, based on uranium-lead data for certain meteoritic components, is about 4.568 maybe billion years. And when did the moon exactly form? Anywhere between 30 and 100 million years from this particular point. So let's say about 4.1. I mean, forgive that, the decimals could be a little bit off because I took it from a website and things are not always updated. So you had formation of the moon, and then you obviously had the magma ocean or the magma sea, and then, the magma ocean crystallized rather rapidly. We know that they crystallized rapidly because anorthosites are as old as 4.456 billion years. And then we think that the highlands are mostly done by about 4.4 billion years, because that's the average age of the highland rocks. And then the lunar mantles was melted by, multiple reasons, and the Mare basalt started forming. So for the Mare basalts, we have ages from about 4 billion years all the way up to 3.2 billion years. And we'll talk about this particular period of lunar cataclysm in a few slides from now. But, we can start, forming what is known as a stratigraphy for the moon. So you had timelines when the magma ocean crystallized to form the highlands, and then the additional mantle actually, further melted to form the basalts, right? And then about 2 years ago, we had samples that were returned from the Chinese mission. This is the first Chinese sample return mission called the Chang'e 5. And they basically, again, sampled this place called Mons Rumka, which is located in the northwest lunar near side, and a few basalt samples basically, yielded an age of about 2.03 billion years. So this is the youngest lunar sample for which we have radiometric age data till date. And so clearly, our understanding of this diagram changes rapidly, right? Based on analysis of one sample. So we know that the mantle continued to melt in the moon to form basalts just about 2 billion years ago from the present day. And so the moon was actually an active planetary body for the first 2.5 billion years of its history. Of course, when I say active, we mean active in terms of, tectonic activities or, let's say, mantle melting. The moon is still, somewhat active because the surface is constantly being modified by, impacts of micrometeorites, right? So that kind of activity is still going on, but not the kind which will actually melt the lunar mantle. Of course, as I said, because of the intensive and study of the impact craters on the moon and additional crater counting. By crater counting, I just mean that if you have a large crater and you have a bunch of small craters in them, those small craters formed after the original crater formed, right? And if based on the radiometric age data that we have for the samples that have been returned, we know the basic age of the terrain, and so we can basically look at the ages of the craters, right? And so crater counting suggests that some of the crusts that we have on the moon could be as young as about 1 billion years or so, but although we don't have radiometric age data for them, okay? And we mentioned about the lunar cataclysm. This is also based on the study of impact craters on the moon, where of course, as expected, early in the solar system, collisions were much more rampant, and so the frequency of impact cratering on a body like the moon, which does not have an atmosphere and hence no frictional heating when a body comes towards it. And that's why the moon actually preserves all these craters, right? So it was very high early on, and it exponentially decayed. So this is the curve to remember. But there are these very large basins on the moon that are, have an age of about 3.8 to 3.9 billion years or so. And that basically suggests that while, most of the debris around the moon was actually being, kind of cleared out, there must have been some kind of a perturbation in, the asteroid belt, right? Which we think is because of orbital migration of these large planets. And then that basically threw out, some of the larger material, again, which eventually collided with the moon to form these large impact craters. So this is a period of late heavy bombardment, which would have affected most inner solar system planetary bodies. Of course, on the Earth, this record is completely nullified because the Earth's surface has been modified over time. In the moon, because of the lack of any, water or, aqueous, hydrocycle or plate tectonics or, an atmosphere, these records are actually very well preserved. Anyway, so now we have an idea of the different kinds of rocks that we have on the surface of the moon and their ages based on radiometric age dating and impact crater studies. And so we can actually put forward a time scale for lunar activity. Of course, this is about 4.5 billion years ago. You had a magma ocean that kind of crystallized, and this crystallization of the magma ocean resulted in the formation of an anorthositic light crust on the top. Of course, the lunar mantle started melting, and the occasional melts that came up formed the basalts or the mares, right? And then eventually, you have this constant, so the volcanism most likely ended around 2 billion years ago, but you still have the surface of the moon being modified by smaller and smaller collisions, which lead to formation of brecciated material and the regolith, which is the lunar soil, right? And this is a nice little review paper that came out about 10 years ago, and I forwarded that as a reading material, just so that you can refer back. Now, when we look at rocks, whether it be on the Earth or on the moon, we are only scratching the surface literally, right? So it basically tells you what's on the surface. And of course, based on analysis of those rocks, we can figure out where they came from inside the Earth's mantle. But that's really not, telling us much about what exactly is in the Earth's mantle. And so we need these, seismic techniques to which basically are, the way these seismic waves propagate through media, and the velocity of these seismic waves will change based on the density of the material and also, the shear modulus. And so Apollo 11 also had a seismic experiment on the moon, and this is an image of that. And subsequently, Apollo 12, 14, 15, and 16 also put in, 3-component long-period seismometers. And this is a paper by Nakamura in 2008, where he actually summarizes 13,000 seismic events that have been detected. And now these are all coming from deep inside the moon. Tells you something about the wave propagation through the interior of the moon, which in turn tells you about what's inside the moon. Gives us an idea, right? And so, but we have to remember that lunar seismicity is fundamentally different, from that of the Earth. Okay, because on Earth, seismicity is primarily because when plates subduct beneath one another. That's one major reason. And but you don't have plate tectonics on the moon, right? And so the seismic sources on the moon could be classified as deep moonquakes, which are mostly coming from, let's say, 700 to about 1,100 kilometers. But about 7,000 of these have been recorded, and they mostly come from what is known as 250 location or nests. But the mechanism is not, plate tectonics. It's majority, correlated with tidal cycles being caused by the Earth and the Sun, and only some may have been triggered by some in situ lunar mantle features. And of course, you have the shallow moonquakes, which are relatively rare, and you have about 30 odd events. There is no connection of the epicenters with any geological and geographic features. This is mostly because of relays of thermoelastic stresses. It could be related to large basins. And of course, you can also have signals being emitted because of impacts, right? And so based on the seismic data, you can actually have some understanding of the lunar interior. People think that the lunar crust is about 30 to 60 kilometers thick. The mantle, again, is very similar to that of the Earth's mantle, olivine pyroxene mixture. And the seismic wave velocities up to 560 kilometers depth are reasonably, homogeneous, and become more heterogeneous below that. And this is primarily because of phase changes, and then there is a seismic attenuation beneath 1150 kilometers or so, which could be correlated with presence of a partially molten region, because that kind of slows down the primary wave velocities and also doesn't allow shear waves to propagate. But the core of the moon is very poorly understood. I mean, it's considered to be very small based on moment of inertia calculations. And remember, the moment of inertia of a perfect sphere is about 2/5 mr squared. And if you have values that are slightly lower than that, it tells you that there has been some, kind of density concentrates within, the interior of a planetary body. And if the perturbation is actually very tiny compared to 2/5, you can say that the moon is actually, the core is actually pretty small. Anyway, we'll talk about, the lunar core from a slightly different angle in another 5 minutes from now. And so now we have a reasonably good idea about the lunar crust based on seismic data. So you have the regoliths and the large-scale ejecta, and there's the crust and the fractured crust, but this is only, about 25-30 kilometers deep, right? We also have other geophysical data, the gravity data, and one important contribution. So this is, coming from these orbiters, Clementine or Prospector, or this Kaguya and Selene, and then more recently the Grail, right? And so, we know that there is a crustal dichotomy on the moon. The near side is actually slightly thinner, or the far side is slightly thicker, but about 15 kilometers or so. And we also find these geoid anomalies. So for the moon, it's actually called solenoid. And these are, geoid is nothing but an equipotential surface. And so these positive anomalies that you find out here, these red circles, are primarily because of the density contrast between the mare basalt fillings of craters, which are surrounded by the less dense anorthositic crusts. Okay, so the last 10 minutes or so, I'd like to give you two or three examples about geochemical and isotopic comparisons between the Earth and the moon, and how they might have some implications for formation of the moon and other processes on the moon. The first thing is, so we're going to look at some siderophile elements. Siderophile means these are, they love metals. So if you have, silicates and metals and melts, these elements will actually partition into the melt phase, right? So like on the Earth, these are mostly concentrated in the Earth's core, like the platinum group elements or some of these transition metals. And we'll also use oxygen isotopes, which is again, the ratio of 18/16 or 17/16. These are all stable isotopes, no radioactive or radiogenic component present in oxygen. So remember, we talked about this giant impact hypothesis and how it suggests that 80% of the moon came from the Mars-sized impact at Theia. Now, if you look at the oxygen isotopic compositions of different meteorites that we have, these are carbonaceous chondrites or iron meteorites, or the calcium aluminum rich inclusions and chondrules that are part of these primitive meteorites or these differentiated bodies. Look at this diagram, and you have this one line called TF, which is a terrestrial fractionation line. That means you take any sample from the Earth, could be water, could be rock, they all plot on this line. And this terrestrial mass fractionation line is mass dependent. That means, this is essentially the 17/16 ratio on the y-axis and 18/16 ratio on the x-axis. Mass difference of 1 and mass difference of 2 on the x-axis. So the slope of this terrestrial fractionation line is about half. Okay. And you'll find that most of the meteorites actually don't plot on this terrestrial fractionation line, and that is, because of other possibilities like this carbon monoxide self-shielding, the solar nebula. Will not get there, but let's focus on the terrestrial fractionation line, and then look at samples that we have from Mars, which are these diamond-shaped objects. Again, they have a slope that is mass dependent, but they don't plot on the terrestrial mass fractionation line, which is this TFL. The triangles out here are samples from these howardite, eucrite, and diagenite meteorites, which are all coming from this differentiated asteroid called 4 Vesta. They also, if you have a best fit line, they'll be mass dependent, but they don't plot on the terrestrial fractionation line. But if you take all the lunar samples and lunar meteorites that we have data for, they all plot on the terrestrial fractionation line. Now, what does it mean? It means that the Earth and Moon are very, very similar in terms of their are essentially identical in terms of their oxygen isotopic composition. But there is no other object that for which we have samples, no other type of meteorite which plots on the terrestrial mass fractionation line. So this is too much of a coincidence. And so one could argue that, well, if we really had a Mars-sized impactor that is Theia, how much of it could be, gone into the moon based on oxygen and stable isotopes and simple mass balance constraints. If you take n-member values of this cap delta 18O, which is nothing but the deviation of delta 18O, delta 17O from the mass fractionation line, we can only get like 2 to 3 to 8% or maybe 5 to 8% of, this impactor going into the moon. That is, contrasts with the 80%, that models actually tell us, right? So the other way to explain this would be that, look, what if the impactor and the proto-Earth actually had the same oxygen isotopic composition? And hence, oxygen isotopes are a poor tracer of how much actually goes into, because, when you're trying to do mixing, the end members must have very different compositions, right? And so if the Theia and proto-Earth, have to have the same oxygen isotopic composition, then they must have formed at very similar distances from the sun. Okay, and remember, we don't have any other planetary body for which we have data which has the compositions like that of the moon, right? So the Theia must have been too much of a coincidence. Additionally, if the Earth and proto-Earth and Theia actually have a very similar composition, then why just oxygen? They should be similar in almost every other element. But we will see that the Earth and the moon are not essentially geochemically identical. There are different, we talked about those, high titanium and low titanium basalts, which are not there on the Earth. We also will see depletion volatiles on the moon that we don't have on the Earth. So this is too much of a coincidence to actually argue that the impactor also had the same oxygen isotopic composition as the Earth. Of course, there was this one interesting paper which suggests that, maybe Theia actually came with a different composition, but after this giant impact, we found a way to equilibrate, the Earth-Moon system in this proto-lunar disk. So this is a post-impact equilibration in a silicate vapor atmosphere after the impact. And this also has its own little drawbacks in the sense that, we have to really transfer the signature of the impactor and equilibrate everything before everything solidifies, right? And things are becoming cold very rapidly. So the time scales of convection within the Earth, within the liquid vapor, from the Earth to this protolunar disk, and then mixing within the disk, they all have to be done very rapidly. And again, one has to remember that even if you homogenize oxygen, why didn't we homogenize every other element? Because the Earth and the moon are not really geochemically identical. So even after 50 years of analyzing oxygen isotopes, for lunar samples and terrestrial samples, we still have this, problem, okay, of similarity between the Earth and the moon, which really does not have a very, very concrete, explanation. We can also look at another aspect on the moon, and that is this volatile depletion. We all know that the volatile elements are low in the moon. The fact that the moon has very, very little water also stems from that. And let's look at one particular element, potassium, which is, in terms of its condensation temperatures, is very volatile. It only gets into a solid phase at very low temperatures, less than 670 Kelvin. And so if you look at the isotopes of potassium, and you specifically looking at the 41/39 ratio, if you look at the potassium depletion in terms of concentration on the moon, you should have an isotopic composition that allows enrichment of the heavier, the loss of the lighter isotopes in the moon significantly. But early studies actually couldn't find any difference between moon rocks and meteorites and Earth. But this is why science is always allows incremental growth. This is a paper very well cited from mid-90s, and then comes a paper from about 10 years ago, 8 years ago maybe, and this is because of improvements in mass spectrometry. This is a multi-collector ICP-MS where they actually demonstrate that the moon actually has high delta 41, which means low 39. This is the ratio, right? So depletion of the lighter isotopes has happened on the moon, consistent with this giant impact, hypothesis, which would have volatilized, some of the, volatile elements like potassium, consistent with the alkali loss. But what it's not consistent with is the extent of difference between the Earth and the moon. And if you really wanted to have a vapor solid kind of a fractionation, as we can model it using what is known as a Rayleigh distillation model, the moon should have been significantly more enriched in the heavier isotopes, somewhere up here. But that's not the case. And this has been explained by the fact that maybe in the proto-lunar disk, the pressures were not really at vacuum. So basically, you need pressures of 10 bar or more to actually subdue this isotopic fractionation. So this is an interesting idea that has been floating around, and since then people have now done even more fancy measurements and found that in some cases you have excesses or loss of the lighter isotopes. But in some samples on the moon, you actually have enrichments in the lighter isotopes on the moon, and that is because of recondensation from a vapor cloud. So you can have an impact that comes and hits the surface of the moon that releases the lighter isotopes because of their high 0-point energy, and then eventually they can recondense into some other parts of the moon. And so this, in the last 3-4 years, has been quite a phenomenal discovery about how these volatile element isotopes behave on the moon. The last thing that I'd like to tell you today is about the siderophile elements. And I mentioned that these are high affinity towards metals. And let's take a look at this figure from the paper by Ringwood and others in the late 60s and 70s. I've actually forwarded those papers. And we can look at these moderately siderophile elements, manganese, vanadium, and chromium. And you can see that this is nothing but the moon by Earth's mantle. So you can see that the values are very close to 1. That means the moon and the Earth have very similar concentrations of some of these elements. Okay. Now, although the moon and the Earth have similar compositions, they are actually depleted in vanadium, chromium, and manganese with respect to these primitive chondritic meteorites, which we think are the starting material of the solar system. That means that some of these elements like vanadium, chromium, and manganese must have, entered into the Earth's core, because what we measure for the moon and the Earth are basically material derived from the Earth and the lunar mantle. So if you put some of these into the lunar or terrestrial mantle, then yes, the depletion with respect to CI chondrites can be explained. But one has to remember that the behavior of these moderately siderophile elements, if you want them to be really entering the Earth's core, you really need specific conditions, like very reduced conditions at high pressures and temperatures when the cores were actually being formed. And so, but the important thing is the fact that the moon and the Earth have very similar concentrations of these elements. One could argue that the signatures that we see in the lunar rocks are actually derived from the Earth's mantle after the Earth's core had formed. So this is where core formation on the Earth and moon formation are actually being considered as almost the same event. We can also consider some of the other siderophile elements which are plotted here, and some of these like rhenium and gold and arsenic and moly and germanium, where you find that the lunar basalts are now becoming depleted in these elements compared to the Earth's mantle. Okay, and this is only possible if you had an additional effect of some of these elements being sequestered into a metal phase within the moon. And this is actually an interesting evidence for formation of a small but a metallic core that is present in the moon, because now the lunar mantle, you started off with Earth-like material, but some of these highly siderophile elements, which have greater preference for metal over silica, so their partition coefficients are even higher, they seem to be depleted in the lunar mantle compared to the terrestrial mantle. And that is because after the moon material was taken out from the Earth's mantle, you had an additional step of forming the lunar core, which basically sequestered some of these elements in the core, leaving the lunar mantle depleted with respect to the starting terrestrial mantle. So this is an interesting evidence of the presence of a small metallic core in the moon. And so with that, I will try to provide you with some take-home messages. And I'll tell you that the giant impact theory best explains the formation of the moon, although compositional similarities or dissimilarities are not completely explained. Except, I've given you an example of the oxygen isotopes. And if you're interested, there are explanations that have been provided in the last few years. I should see some of the newer papers by Mattia Cook and Sarah Stewart, or even Robin Canup. There was a series of papers in Science where they actually argue that, look, the compositional similarity can be there, but we have a problem with this, angular momentum issue of the Earth-Moon system. But if you actually spin the Earth much more slowly when the moon just before the impact, we could possibly consider some of these, geophysical observations and geochemical and isotopic observations to come together. We find that the lunar rocks basically have a unique assortment of minerals and rock types, and that requires a lunar magma ocean and a density overturn. We also found that the age of the moon, of the lunar rocks, suggests that the moon was formed within the first 100 odd million years of the solar system. It could be anywhere between 30 million years and 120 million years. So if you want to know a little bit more, you can read up papers on hafnium tungsten isotope systematics. These are what are known as short-lived radionuclides, because 182 hafnium decay to 182 tungsten with a half-life that is about 9 million years or so. So it basically tracks processes in the first 50 odd million years of the solar system. Today, we don't have 182 hafnium, but we have excesses of 182 tungsten in planetary material. And so then we found that geophysical data will provide us interesting insights into the lunar interior. And we also have this crustal thickness dichotomy. We definitely have volatile loss and formation by giant impact, which are reasonably well constrained by modern day measurements of potassium stable isotopes. And finally, the siderophile element concentrations, they basically put forward constraints on core formation on the moon. So with that, I'm going to leave you with this little quotation, and that is these lecture series. I think the START program is basically the way I understand is to provide people with information. So what Albert Einstein had said, that the more that I learn, and the more I realize how much I don't know, and that is what pushes people to do science, right? So if everything was understood, then there's no point in proceeding further. And the pictures at the bottom, the animations at the bottom also tell us the same thing. 1969 was the first time when we actually had samples being returned from the moon, and that's about 54 odd years ago. We are still finding ways of sending spacecrafts that will, keeping my fingers crossed, land on the surface of the moon and provide us with additional data, because we still don't know much about the moon, and this is where I think the future lies. So we need to have, more and more science discussions, find out important, science questions, set up, excellent facilities within the country that will actually, eventually when samples are returned by, ISRO missions, we will be ready by then. So with that, I'll just, this is a teaser, and I'll be happy to take questions. Thank you.